My name is Michael Barker. I am a professor of civil and architectural engineering at the University of Wyoming, but I'm also the director of education for the Short Span Steel Bridge Alliance. And as we go out and we talk to counties and municipalities and state DOTs, a lot of issues come up like life cycle costs, and I'll be talking about that on June 10th. But this one that Mark just presented, sustainability, is going to become more important. And so the Alliance decided to do a study here at the University of Wyoming with the people that you see the pictures to the right. Those are three of my students, and that's me on the left, where we actually took two nearly identical bridges and just said, okay, let's apply these EPDs. Let's look at these materials and all that kind of stuff, and let's just do a sustainability study. And so that's what we're going to look at here. The objectives of the study was looking at a life cycle sustainability assessment from cradle to grave of two nearly identical or functionally equivalent two-lane bridges from Whitman County, Washington. They're rural bridges. The first one is a steel bridge called the Celtis Warner. It was built in 2020. It's a little over 35 foot long. It's a modular steel, 7-rolled beams, corrugated gravel deck, and the county crew built this bridge out of Washington. The other bridge we're going to look at is a concrete bridge called the Thornton Depot. It was built in 2019. It's right at 34 feet long. This one was made up of precast, pre-stressed beams, modules. There were 8 of them set side by side and welded together. And so the concrete deck, of course, were these beams. But the county crew also built this one. And we're looking at life cycle sustainability assessments. So we're going to be looking at putting the bridge in and maintenance over the years and even demolition of these two bridges. And then after we looked at those two bridges, it's like, how do we use this? And so our group developed procedures for owners or society that can consider sustainability benefits when selecting which bridge to use in the design. So here are the two bridges, the steel Celtis Warner on the left, the concrete Thornton Depot on the right. And we are going to look at the superstructure itself and the sustainability aspects of construction and maintenance and demolition of those two bridges later on. Now we're only going to look at the superstructure because these bridges are functionally equivalent. Because one's just a little bit longer than the other, we do have a length adjustment, but almost identical. You could pick one up and put it on the other abutments almost. And we wanted to look at just the superstructure. Both bridges were assumed to last 75 years. They are both prefabricated bridges with the modular steel beam and the modular concrete beams. And looking at the installation equipment and all the costs associated with that. Then the maintenance was assumed identical for both bridges, where there was no maintenance for the first 25 years and then yearly maintenance for the next 50. But since it was assumed identical for both, it's not going to impact the comparison. Now, when in 75 years, when these two bridges are demolished and replaced, we look at estimates from the county for demolition equipment and costs, which do differ between the two bridges because the concrete bridge is very heavy and very voluminous, and the steel bridge is going to be taken apart and recycled, as we will see. So the process of the study was first to develop that life cycle sustainability assessment, which means establish criteria and benchmarks to how to measure sustainability, which of course includes the greenhouse gas emissions, but we also looked at energy consumption, and one of the criteria was recycling and waste stream metrics. And then of course, we get the life cycle bridge results. Then we developed that procedure that considers sustainability benefits for the decision making in the design of bridges, where we monetize the sustainability benefits and create an equivalent cost decision-making process. So to figure out what criteria we're going to use and the benchmarks and all that kind of stuff, we started with well-known international systems with the LEED rating system or the Envision credit list, and looking through all the sustainability aspects that those consider. and said, you know, bridges don't have windows, bridges don't have air quality, bridges don't have light and all that kind of stuff, and leadership. And so it really came down for rural bridges, very simple rural bridges. We came up with 4 sustainability criteria: emissions, energy consumption, recyclability and waste management, and of course, life cycle costs to compare it to. So when we look at emissions and energy consumption benchmarks, we're talking about what it takes in terms of embodied emissions and energy consumed to produce those superstructure materials and the fabrication of those bridges. And then we have to put those bridges into service, so we have construction equipment. Then throughout the life, there's maintenance equipment that have embodied emissions and energy consumed. And when that bridge is demolished for the new bridge to go in, there's the equipment there that has emissions and energy consumed. For recyclability and waste stream management benchmarks, the use of recycled materials is really in the EPDs, but recovery of those recycled materials during demolition is an important aspect to sustainability, because what is not recycled must be sent to the landfill. So those are important benchmarks for the recyclability and waste management criteria. Life cycle cost is just what it sounds like. We need to have a life expectancy of the project. These were both assumed to last 75 years. But with each of those bridges, there's an initial cost, there's a maintenance cost, there's a demolition and salvage or landfill cost, which then is brought back with an appropriate discount rate to a present value life cycle cost that we can use in the criteria. So Mark talked about EPDs, environmental product declarations. And so the first thing we did is we went out in search of what materials are put in these bridges, and how do we find out what are the embodied emissions in producing that bridge, and what is the energy consumption in producing that bridge. And we found it in component EPDs, where this top table shows us precast concrete component has so many emissions per ton and so much energy consumption of kilogram CO2 equivalent, and energy consumption per ton of megajoules. And steel has different values for different types of steel members. And then we even had gravel on one of the bridges, and that has associated emissions and energy consumed to extract, really not fabricate for gravel, but extract, transport, and put into place. But we also looked at the construction and the maintenance and the demolition equipment costs. And so we divided equipment up into light equipment and heavy equipment, as shown in this bottom table here, where for each hour of running that equipment at working speeds, we have emissions and energy consumed. So with these metrics, now we can apply it to the bridges, the construction, the maintenance, and the demolition over the whole life cycle of those 2 bridges. And here it is for the superstructure, putting it in place. And at the top is the steel bridge, and at the bottom is the concrete bridge. And so we break up the different components of those bridge into a weight. Then we bring over the appropriate embodied emissions and energy consumed. There is a length factor. The steel bridge was a little bit longer than the concrete bridge. So the components that are dependent on the length are multiplied by a ratio of those lengths, or 0.953 you see in the yellow here. And then we can calculate the embodied emissions and the energy consumption of those components and add them up at the bottom in the green. Now, this is a pretty nice spreadsheet that we developed to where we can handle pretty much any bridge. And when you see yellow, that's an input from the user, and these grays come from linking it back to the EPDs that we saw on the previous page. So we see the totals for the superstructure for the steel bridge on the top table and for the concrete bridge on the bottom table there. Then we have the emissions and the energy consumption for the equipment usage. I have two sets of three tables here. The top three are for the steel, the bottom three are for the concrete. We have construction, maintenance, and demolition. And the idea is the same. We got estimates from the county engineer from Whitman County, Washington on what it took to construct the bridge. Then we got hours estimated for the maintenance for the last 50 years of the bridge, and then estimates for the demolition. And then we have a usage factor. When we build a bridge, you know that that equipment is not used 100% of the time, and so we had estimates for the usage factor. And so we can get totals for emissions and energy consumed for the construction, maintenance, and demolition equipment. And now we take a total of that. This is the first results that we see from the study of the two bridges. On the top, it's the emissions table where we have steel and concrete. For the superstructure only, for construction, for maintenance, we see the maintenance is the same because the maintenance was assumed the same for the two bridges. For demolition, we see that the steel was a little less because of the lighter weight. For the superstructure, the steel was 68% of the concrete. The construction was a little bit less for a total. So over here on the right of the top table are the totals, and we see that the steel bridge has 79% of the embodied emissions of the concrete bridge over the life cycle of the bridge. Below is the energy consumption, which is related, but when we start talking about renewable energies and non-renewable energies, this might become an important criteria. But we see the steel is 89%, the concrete on the superstructure, less for the construction. Maintenance, again, is the same. Demolition, a little bit less. And the totals, it's 92%. So this is our first results comparing these two particular bridges where it says this steel bridge has sustainability advantages over this concrete bridge. Remember, we have a recycling criteria. So Mark told you that steel, especially the main steel structural components, he said 97%. I have 98% up here. 98% of the steel is going to be recycled. And somebody is willing to pay us for that. And the going rate in the state of Washington was $100 per ton when we did the study. Now, Whitman County is not planning to or currently does not recycle concrete, but there are studies that a lot of concrete is recycled, about 80% in the United States. And so we assume that here for a more fairer comparison between the steel bridge. So 80% of the concrete was assumed to be recycled, but nobody's willing to pay for that. You still have to pay somebody else to take it to recycle it. And that's $4.10 per ton in Washington. However, that's a lot cheaper than sending all of that concrete to the landfill, because the landfill costs $75 per ton in Whitman County. And so now we have three tables here. The top table looks at the steel and the concrete again, has the steel weights and the concrete weights, what percentage is recycled in the yellow that we can change, and then how many tons are recycled and how many tons are sent to the landfill. And the steel that's recycled, there is a benefit, you get paid for it. And for the concrete that's recycled, there's a cost of $4.10. And then anything that gets sent to the landfill costs $75 per ton. So now we come to the bottom tables. The left is the steel bridge. The green means we actually get paid $1662.49, and the landfill costs come out pretty cheap because almost all of it's steel. For the Thornton Depot, yes, we are recycling a bunch of concrete, but we have to pay to even recycle it, and then the rest gets sent to the landfill. Now, these can be brought into a present value cost analysis using an Office of Management and Budget discount rate of 1.7%. There's three tables for each bridge. The top left is for installing the bridge in the beginning. Then right below that, you have the maintenance with estimated costs from Whitman County, brought back to current costs down there in the green. Then to the upper right, you have demolition with the cost for labor, equipment, and that's where we would gain some salvage money or pay for landfill costs. And those are all brought back to a present value cost in the green. And then that's repeated for the concrete Thornton depot below. And so these are the results of the life cycle costs. The second result we get from this study, where the steel is on the top and the concrete's on the bottom, for putting the bridge, or I'm sorry, for the prefabricated bridge, the steel has 78% of the concrete costs. For the total initial, this includes the construction costs and the gravel costs and that kind of thing. For putting the bridge in place and opening it up, that's what total initial is. The steel is at 80%. Then present value for maintenance is the same because we assume the same for both. And then the demo costs for the steel bridge is less just because we are getting that benefit for the salvage. Somebody's paying us for the steel and we don't have as much going to the landfill. And then of course, the right column is the total present value of the life cycle costs, where steel is at 81% of the concrete. So second result, for this steel bridge and for this concrete bridge that we looked at, the steel bridge has lower initial and life cycle costs. So now, how do we use this in a design decision-making process? What I'm going to show you, the report, you can find the full report on shortspansteelbridges.org, and that goes through a benefit cost analysis and an incremental benefit cost analysis. But it really led to this, where we monetize the sustainability benefits of one bridge over the other. Because sustainable design is predicated on the idea that society is willing to pay extra for reducing harmful effects on the environment, reducing CO2 emissions, reducing energy consumption, increasing recyclability rates. Now for these two bridges in the blue here, the decision is trivial. Steel had higher sustainability benefits and steel had lower initial costs and life cycle costs. So there's no decision required. If we were comparing these two bridges, the steel bridge should win on both cost basis and sustainability basis. But what if the steel bridge had cost more than the concrete bridge? What if the steel bridge had cost $5,000 more than the concrete bridge? How do we measure those sustainability benefits and put it into a decision-making process? So considering sustainability in the design of a bridge entails answering the question, what additional costs would society or the owner be willing to pay to increase sustainability benefits? And now I'm just going to play a game. I'm going to say, suppose society is willing to pay 20 cents per kilogram of CO2 reduced, and 4 cents per megajoule of energy reduced, and $50 per ton of landfill reduced. Now, these are just guesstimates. Don't take these as gospel or anything like that. This is for demonstration purposes. Then, an equivalent cost can be determined for any number of design alternatives, where the basis of the analysis is the lowest cost alternative. And we calculate an equivalent cost here in the blue, where we take that initial cost, or we could even use life cycle costs. And then we start subtracting off if an alternative reduces the CO2 emissions, or if that alternative reduces the energy consumed, or that alternative reduces the amount of material that goes to the landfill times their respected acceptable costs. Then the lowest cost alternative is chosen considering the sustainability benefits and cost of that alternative. Now, this actually is an incremental benefit cost analysis that is hidden in terms owners and society can understand. Because owners and society is, what's the first cost? What's the life cycle cost? Let's make the decision on that. Here's an equivalent cost that considers sustainability that would work the same as an initial or life cycle cost analysis. So I just show it by a demonstration here. Table on top says I have 5 alternatives I'm considering for this bridge project. The lowest cost one, alternative 1, is the basis for the analysis. It costs $100,000. And then it has, through like the spreadsheet I showed earlier, a certain amount of embodied emissions, energy consumed, and land material sent to the landfill. And then alternative 2 costs more. Alternative in 3 costs 105,000. Alternative 4 and 5 costs 107,000. Okay. And they have their emissions, energy consumed, and materials sent to the landfill. So using the lowest cost alternative as the basis, we can calculate, okay, how much does alternative 2 reduce emissions? It doesn't. It actually increases emissions. So that's a negative. How much energy does it reduce? Well, it does that, and it does reduce landfill costs. And then we can calculate a cost benefit to that based on 20 cents per kilogram of CO2, 4 cents per megajoule, and $50 per ton, and then come over and find a total cost benefit to find that equivalent cost. So now let's look at a couple of these. Alternative 3 has the lowest equivalent cost at $99,179. That's the initial cost, but it got a $5,821 cost benefit for reducing sustainability harmful effects. Okay. Now, alternative 1 is the lowest cost with a basis with a basis total cost benefit of 0. So it comes in at 100,000. Alternative 4, if you look at that one in the orange over here, has the highest sustainability benefits at $59.56. But it costs $7,000 more than alternative 1. That's an incremental benefit cost less than 1. The sustainability benefits are not worth the extra cost. So now let's look at alternative 3, because that's the one we should choose. It costs $105,000. It has $58.21 of benefits for an equivalent cost of $99,179, the lowest of the 5 alternatives. That one should be chosen. But what happens is society is getting $5,821 of sustainability benefits, and it only costs $5,000 more. That's an incremental benefit cost greater than 1. The sustainability benefits outweigh the additional costs. And then alternative 2 and 4, the additional sustainability benefits, if any, we saw one where it was actually negative, do not outweigh the additional costs, so those would not be chosen. So alternative 3 costs $5,000 more, but has a societal accepted rate of return of $58.21. Again, this is incremental benefit cost analysis with monetized sustainability benefits. The owner or society determines the acceptable cost for those sustainability benefits. And the owners understand this equivalent cost because it's very similar to, or more or less identical to, a comparison based on initial costs or life cycle costs. So getting to some summary and conclusions, the results of these 2 bridges, the steel Celtis Warner and the concrete Thornton Depot bridges, is that for the installed bridge, steel has 30% less emissions. Steel had 11% less energy consumed. For the whole life cycle, steel had 21% less emissions. And like Mark did, that's equivalent to 31,300 equivalent vehicle miles. It has 8% less energy. That's 0.6 homes for a whole year. And for costs, steel had 22% less prefabricated bridge costs. Steel had 20% less installed initial costs. And steel had 19% less life cycle costs. And now to finish out that equivalent cost procedure, it is similar to initial cost or life cycle cost decision making. The owner or society drives it with acceptable sustainability benefit costs. For instance, if they didn't think that saving a megajoule of energy was worth anything, then that's a 0. If they're only interested in CO2 equivalent emissions, that's what you use. It's flexible in the analysis details to where you could look at the structure only or the structure and equipment. You could look at initial costs or life cycle costs. You could look at only the prefabricated bridge or the installed bridge or the life cycle bridge. And you could do it with or without maintenance and demolition. You could use any combination of emissions or energy consumed and landfill use, or others could be added if there's something else that somebody thought this is a criteria that we want to have in our decision-making process. And then we consider total energy consumed, but in those environmental product declarations, They do break it down into non-renewable energy used and renewable energy used. So you could look at only non-renewable energy used, where it comes down to an equivalent cost that says we will look at the agency costs or the initial costs or life cycle costs, and we will consider that we are willing to pay for reduced emissions, reduced energy consumed, or reduced material sent to the landfill with an acceptable cost to compare two or more alternatives. And with that, I would like to thank some folks at AISI, Mark, which you heard about earlier, and Dan, who is online here. Whitman County, the county engineer and the assistant county engineer were instrumental in getting us the material and making some estimates. And then I also had some people that specialized in sustainability here at the University of Wyoming that helped guide this research.